Right, let's get started. So, hello everyone. This is SeungryongKim. So this is lecture 5. In this lecture, we discussed what is the linear independence and what is linear transformation. So, yeah, let's recap. Here, right? So, in lecture 4, we discussed the chapter 1.7, 1.8, 1.9. So the chapter 1.7 was the linear independence. So we discussed the concept of linear independence, right? So the vectorization has only trivial solution. We just say that the set of the vectors is linearly independent. Otherwise, if there is the non-zero vectors as a solution, we just call this is linear independent. This vectorization, in this case, the vectorization is called the linear dependence relationships. So, yeah, we discussed how to find the linear dependent relationships like this. This is not a unique solution. I mean, there are infinitely many solutions, though there are infinitely many possible linear dependent relationships among the vector set. Yeah. So when you think about the matrix and the matrix consisting of the column vectors, then the matrixcation A is equals 0 can be written as a vectorization. Then we can say that similar things, each linear dependent relationship among the columns of matrix A corresponding to the non-trivial solution of A is equals 0. So, right. And we also introduced the theorem 7, characterization of the linearly dependent set. Indexes set S of 2 or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others, right? We proved this one, right? So, yeah. And we also discussed one example. Okay, we have a two vector set. I mean, just two vectors, u and v. Describe the set of this span by u and v, so span of uv, and explain why the vector w is in span uv if and only if uvw is linearly dependent. 그렇죠? 그래서 linearly dependent 하면은 w가 스pan 안에 들어가더라. 이거를 우리가 이제 theorem 7을 통해서 증명했었죠. 그렇죠? Like this. Okay. So today we will introduce the two more theorem in chapter 1.7. This is chapter 8. So if a set of the vectors contain more vector, then there are entries in each vector. Then the set is linearly dependent. In other words, any set V1, V2, Vp in Rn space, so each vector defined in Rn space, and number of vectors are p, right? This set is linearly dependent if p is larger than n. So, first of all, let's think about such matrix. So let's think about matrix that consisting of this kind of vector set. So let's say A, consisting of the column vector v1, v2, vp. So in this case, what is the size of this matrix? So what is the size of this matrix? 뭐죠? 자, each vector in Rn space, then there are p kinds of vectors. So in this case, size of this matrix A is n by p, right? n by p죠. 그렇죠? And n by p, right? If A is n by p, the matrixcation A is equal to 0, corresponding to the system, linear system of n equation in p unknown. 그렇죠? n equation in p unknown. Why? Because we have okay. So shape of this matrix A looks like this. For example, V11, V12, blah blah blah, V1N, V21, V22, blah blah, V P1, V Pn, looks like this. Then we have an equation and p variable, an equation p variable. If p is larger than n, then there are more variable than equation. So there must be free variable. Why? Okay, so our matrix in this case looks like this, right? Because the p is larger than n. Okay, so here is the one of the p of variable, maybe here, but because the p is larger than n, the remaining column does not have any pivot position, so this column may be free variable, right? So because we have the free variable, we already know this ax equal 0 has non-trivial solution because it has a free variable. So we can represent infinite many solutions in terms of the free variable, right? So it has a non-trivial solution. So COSE of matrix A is linearly dependent, so because we have a non-trivial solution. This is theorem 8. This is very straightforward, right? One more theorem is theorem 8, theorem 9. If a set S, which is that V1, V2, Vp in Rn space contain a zero vector, then the set is linearly dependent. It's very, very simple. This equation, this theorem is very, very simple. Let's suppose that Vn is equal to 0. Vn is equal to 0 vector. Then the equation 1 times V1 or the C times V1 plus 0 times V2, blah, 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 0 times Vp is equal to 0 shows that S is linearly dependent. Why? The solution of this one is going to be C1 is equal to 1, C2 is equal to 0, blah, blah, Cp is equal to 0, right? So it's not a trivial solution. This is a non-trivial solution. This is a non-trivial solution. So in this case, the set is linearly dependent if the set contains a zero vector, right? Okay. So this is the chapter 1.7. Then today we will move to the chapter 1.8, Introduction to Linear Transformation. So what is that? So motivation is like that. We already discussed matrixification A equals B and vectorization x1a1 xnan is equal to B was merely a matter of notation, right? So they are equivalent, right? We already know, right? However, in a matrixification A equals B, we can think of the matrix A as an object that act on a vector X by multiplication to produce a new vector called AX, right? In other words, in matrixification A equals B, we can think of this matrix A is some kind of transformation that act on vector X to the new vector AX, something like this. This is kind of transformation. Then from now on, we will consider this vectorization or AX as a transformation of X by matrix A. So to understand this, we can define mapping a vector by matrix. In this case, maybe vector is X and matrix A, right? Mapping a vector by matrix A. So it's going to be AX. AX is a linear transformation. So let's think about what I mean. So here is a two-vector equation. Maybe this is A, X, P. And here's another equation, A, X, 0, right? So in this case, left equation, left system means, what is the difference between the left system and right system? Right system? A and X is equal, A is equal, but here is a B on right hand side, but in this case, here is a zero vector, right? So left system means homogeneous system. And right system means homogeneous system. Homogeneous system, right? Then let's think about the relationship between this kind of non-homogeneous system and homogeneous system. Oh, okay. So first of all, if we consider multiplication by A as AX, then we can represent non-homogeneous system as a mapping relationship between X to B, like this. So in this case, X was 1, 1, 1, 1, A was 4, -3, 1, 3, 2, 0, 5, 1, and P was 5A. So we can represent this non-homogeneous system relationship looks like this. What about linear homogeneous system equation? So in this case, the solution, let's say this one, 1, 4, -1, 3, 1, 4, -1, 3, and multiplication by A is going to be zero vector here, right? So this one, bottom relationship represent homogeneous relationship. In other words, in this figure, we can consider this matrix equation AX is a transformation between some vector in R4 space to the another vector in R2 space. In other words, some of the vector, let's say x1, x2, x3, x4 to the another vector in R2 space. For example, let's say x1 prime, x2 prime, looks like this. Then matrix A is a mapping relationship between the R4 space to the R2 space, right? So from now on, we will introduce the transformation, concept of transformation, which is also called the function or mapping denoted by T from Rn space to the Rm space is a rule that assigns each vector x in Rn space to the vector Tx in Rm space. In other words, let's say this is Rn space, because if n is larger than 2, we can't larger than 3, we can't draw anymore. So let's just draw as a cloud like this. And let's say here is another space or M space. The transformation T is a function or mapping that assign each vector x in Rn space to the another vector in Rm space as a Tx by transformation T, right? In this case, we define a two definition. In this case, Rn here, Rn is a domain of T. And in this case, Rm here is called codomain of T. Codomain of T. Codomain of T. Codomain of T. So the notation T from Rn to the Rm, T equal to Rn to the Rm indicate that domain of T in Rn and codomain is Rm. Looks like this. So this is definition of the transformation. So today we will see matrix equation AX is one of the transformation. So we can consider our AX as a transformation or function or mapping. Then we will consider some technique defined in the transformation to solve the AX. Okay. So one more thing is that for X in Rn space, 그쵸? Here, X in Rn space, a vector Tx in Rm space is called image of X under the action of T. What does it mean? Okay, so let's say Rn, in this case, this mapping function T, Rn was the domain and Rm is a codomain. But the output of Tx is not always Rm, right? In many cases, Tx, the possible output of the transformation T is going to be the subset of the Rm, subset of the Rm, right? So in this case, this region, possible Tx region is called the range. And this Tx, the point in range is called image of vector X, and this one is called range. This is just definition. So when you think of one transformation T from Rn to the Rm, you have to consider what is domain, codomain, range of the T. Okay? This is just definition. For X in Rn space, Tx is computed as Ax, where A is n by n matrix. What does it mean? Okay, let's think about matrix Ax, right? So we know matrix X is in Rn space. So Rn space means Rn by 1 space, right? And matrix A means A in m by n space. So we already know the output vector P should be in Rm space, right? So this matrix A transform X in Rn space to the P in Rm space. So A is one of the transformation. For simplicity, we denote such a matrix transformation by X to the Ax from now on. X to the Ax. In this case, domain of T is Rn because this is Rn, where n has n columns. The codomain of T is Rm space, when each column A is n entries. So because A is n by n cases, then domain of T is Rn, codomain of T is Rm. Now, one more thing is that the range of T is the set of the whole linear combination of the columns of matrix A, because the each image Tx is one of the form of the Ax. So in other words, okay, our Ax is the image, 그렇죠? Image Ax can be written in a matrix equation x1 vector a1 plus x2 vector a2 plus xn an. Then this one is a linear combination of the columns of matrix A, right? So this is a linear combination of matrix A. So in other words, range of T is a linear combination of the columns of matrix A, or which is the span of A1, A2, AN, right? This is just definition. So range of T in matrix equation case, the set of the linear combination of the columns of matrix A, so which is a span of A, columns of matrix A, right? Question. This is just definition. 자, 오늘 이제 여러분 우리가 또 새로운 컨셉트를 배우고 있어요. 그쵸? 뭐 도메인. 이제 우리가 뭘 하고 싶은 거냐? AX equals B를 풀 때 A라고 하는 거 어떤 트랜스포메이션으로 한번 이해를 해보자라는 거예요. 근데 이제 트랜스포머를 이해를 해보려고 하니까 노테이션들이 필요한 거예요. 그래서 트랜스폼이 시작되는 도메인을 우리는 도메인이라고 할 거고, 트랜스폼이 들어오는 도메인을 코도메인이라고 할 거고, 트랜스폼의 경우의 수, 그러니까 어떤 x라는 의미의 벡터가 어떤 이 코도메인에 떨어지는 점을 tx, 결국 ax겠죠? 그리고 ax를 이미지라고 할 거고, 파서블한 ax를 이제 range라고 표현을 할 거예요. 그리고 이제 우리가 이런 매트릭스 트랜스포메이션을 이해해보자라는 거예요. 그리고 다 데피니션이에요. 그냥 왜 그러느냐, 왜 range라고 하느냐, range라고 부르기로 약속을 한 거예요. 됐죠? Question so far. 뭐 어려운 내용 없죠 지금까지? 없죠? Okay. So let me show you example. Let matrix A 1 3 negative 1 negative 3 A 5 7 and vector U was 2 by 1, P was 3 by 3 2 negative 5, C is 3 2 5. Define a transformation T from R2 to R3 by Tx equal AX. Tx equal AX. So that Tx equal AX, and because A was here and X was here, then we already know A times X is this one. 그렇죠? By 무슨 by which row? Row by column row. 그렇죠? Row by column. So this value is going to be the, 이거 알죠? 우리 했었죠? This value is going to be the 1 times x1 negative 3 times x2. So looks like this. And looks like this and looks like this. So this is Tx or Ax. Tx or Ax. Then we have 4 kinds of question. First of all, find the T of U. Find the T of U, the image of U under the transformation T. So T of U, which 결국 AX가 찾아가는 거고, 두 번째가 find an X in R2 space whose image is under T is B. So T is B. Either more than one X whose image under T is B. Determine if C is the range of transformation T. Range of T. So let me solve each problem. So first of all, first question is find the TU. 그렇죠? Find the TU, AX를 푸는 거죠. So this is AX, 그렇죠? So AU, 그렇죠? TU, 그렇죠? 미안해요. Image of U니까 TU is equal to AU. So A was looks like this, U was looks like this. So our AU is going to look like this. So Y5 by row column multiplication law. So 1 by 2, negative 3 by negative 1. So it's going to be 5 and 1 and negative 9. And negative 9. So this kind of question, this kind of transformation defined looks like this. So our domain, in this case, domain was R2 and codomain is R3 because this is domain, this is codomain. So one of the vector, in this case U, 2 by -1, transform to the one of the vector in R3 space, which was AU, which was 5, 1, -9. Right. This is image of U, image of U. Right. The second question is find an X in R2 space whose image under T is B. So the question was that, okay, here is the one of the vector P, one of vector P in codomain. What's the P? 3, 2, -5. 3, 2, -5. The question is, what is the vector X that can be transformed to the 3, 2, -5? 3, 2, -5. This is second question. So in other words, which X make AX equals B? So in other words, AX equals B. Which X make A times X is equal to B. So in other words, this is just the linear system of A, B with X. So this is just the solution of this linear system. So let's find this solution. Okay, to that, just rule reduce the augmented matrix as we done so far, right? So this is augmented matrix of this linear system, right? So let's do that. Let's row reduce to the REF form, to reduce echelon form. Let's suppose that this R1, R2, and R3. We already know how to do that, right? So first thing we can do, have to make these two terms as a 0 by R2 minus 3R1. This term is going to be R3 plus R1, right? And make this term as a 1 again, because we want to REF form. So by dividing by 14, then eliminate this term as a 0. So it's going to look like this. And because we require REF form, we can further eliminate this term as 0 by using this second equation. So it's going to be our REF form. So here we already know x1 is equal to 1.5, x2 is equal to -0.5. So our x is equal to 1.5 and -0.5. So image of x, this x under T is given vector B. So in other words, here, in this case, x is 0.5 minus 0.5. 1.5 -0.5. So this x can be transformed to the B under this transformation A by matrix A. Okay. Third equation was that either more than one x, then whose image under T is B. So in other words, more than one x means the solution is unicorn. So this is uniqueness problem, right? So in other words, any x whose image under T is B must satisfy equation 1, 그렇죠? equation 1, 이 equation 1을 satisfy 해야 되는데 from 2, equation 2, let's say this is equation 2. It is clear that equation 1 has a unique solution. So there are exactly one x whose image is B. So in this case, only 1.5 0.5 is the only vector S that can be transformed to the vector B under the matrix A. So this is a unique solution. So this is the related to the uniqueness problem. Is P the image of a unique X in Rn space? This is the, from now on, this is a uniqueness problem. So finally, determine if C is the range of the transformation T. If C is the range, C is in range of transformation T. When C is a 3 to 9. How can we do that? If vector C is in the range of T, the C is the image of some X in R2 space, that is C is equal to Tx for some X. This is another way to asking if the system Ax equals T is consistent or the having solution. Solution exists. Existence죠. Solution existence of Ax equals C problem. Given A and C. So let's solve this one. So this is A, this is C. So to find out solution, row reduce such a augmented matrix. So let me do that. R1 is here, R2 is here, R3 is here. Let me eliminate these two terms, right? How to do that? Our new R2 is going to be previous R2 minus 3 R1, and R3 is going to be R3 plus R1. And we further row reduce and finally achieve this one. This is just EF form. Just EF form, but we already know from this EF form, we already know this system does not have any solution. Why? Because of this last term. 그렇죠? Because our previous theorem that say that if the last row in EF form has 0, 0, 0, 0, 0, 0, 0 and non-zero value, looks like this, 0, 0, 0, negative 35, then this equation should be 0 is equal to negative 35, so it's not possible. So we can say that the system is inconsistent. So system does not have any solution. So C is not the range of T. C is not range of T. So it means that if the range here, range is subset of the Rn space, then C is outside of range. So when C is equal to 3 to 5, then C is outside of range. Okay, 자 이거 이렇게 다시 그릴게요. Range of T or matrix A. Okay, so C is outside of range in this case. Then, in other words, Ax equals C does not have any solution. So it means that there is no mapping values that make Ax equals C. So there is the outside of range, outside of domain. So there's no possible X that can be transformed to C by matrix A. So this is a way to understand your transformation, matrix transformation AX. 그렇죠? 이해되죠? 그래서 이제 우리가 지금 뭘 하고 있는 거냐? 어떤 AX라고 하는 거, 우리가 뭐 정말 간단한 이런 거죠. A와 X를 곱하는 2x3와 2x1 벡터 X를 가지고 3x1 벡터를 만들어내는 이 매트리스 이퀘이션을 이제 우리가 이런 식으로 얘기를 할 수가 있다. 트랜스포메이션의 관점에서. 그렇다 그러면 솔루션이 없는 경우, 자, B 어떤 A 스콜스 B에서 B가 여기 찍혔으면 솔루션이 없는 경우다. 즉 레인지 안에 못 들어왔으니 우리 방금 얘기했던 것처럼, 또는 B가 여기 들어와 있으면 솔루션이 있을 거다. 근데 솔루션이 하나냐 여러 개냐가 결국 이 릴레이션십을 보면서 우리가 정할 수 있더라 라는 거죠. 즉 우리가 이제는 AX라고 한 트랜스포메이션을 레인지, 도메인, 코도메인, 레인지, 이미지와 같은 새로운 노테이션들로 얘기를 할 수 있게 된 거고, 그 노테이션들을 가지고 우리가 결국에 뭘 하고 있는 거예요? 계속 솔루션의 existence, 그다음에 솔루션의 uniqueness를 결정을 내릴 수가 있더라 라는 거죠. Question. Today there's not enough question today, so please give me a question if you have. Is that clear? 여러분 따라올만 해요? 아니면 좀 어려워요? 어려울까? 예담 학생이 가장 첫 번째 대답을 했으니까 예담 학생. So is that clear for you? 형민 학생. So it's so difficult. Okay. Other? Okay. Other student? Others? 어려운데 좀 어렵구나. 조금 천천히 갑시다. 오케이. Let's 돈다. Here. 그쵸? Image of T. Image of X under T. Under T. So, let's suppose that T is the arbitrary transformation that transform some vector X to the another space. Let's say Tx, T of X. But in this case, this is general linear transformation. But in this case, we define this this T of X as a AX, A times X. Right? In this case, image of X under T means just AX, just AX. 한국어에서 설명하자면 뭐예요? 그러니까 우리가 이제 T라고 하는 리니어, 그러니까 제너럴한 어떤 리니어 트랜스폼이라는 게 있는데 그 트랜스폼은 어떤 X라는 스페이스, 그러니까 X가 정의된 어떤 RM 스페이스의 어떤 벡터 X를 다른 스페이스, RM 스페이스로 옮기는 하나의 어떤 트랜스폼이라고 가정을 해보자라는 거죠. 그때 뭐 RM 스페이스가 도메인이고 RM 스페이스가 코도메인이고 뭐 이런 것들이 나오는데, 근데 이때 이미지라는 게 뭐냐면 첫 번째 결국에 이미지란 뭐냐면 이 x를 이 tx로 옮겨갔을 때 그때 그 점의 벡터 값이 이미지예요. 이미지라고 표현해요. 벡터. 그 벡터를 이미지. image of x under t. 그렇죠? 근데 우리가 이제 이 tx를 우리는 매트릭스라고 생각해 보자라는 거죠. 결국에 어떤 매트릭스 A를 X에 곱하면 똑같잖아요. 결국에 어떤 Rn 스페이스에 정의된 거를 M 스페이스로 옮겨준다고 생각할 수 있잖아요. 그렇죠? 그러니까 결국에 뭐예요? 매트릭스 A가 하나의 트랜스포메이션이다. 그게 뭐예요? 결국에 이 TX가 결국에 AX랑 똑같다. 라는 얘기를 지금 계속 하고 있는 거예요. Right. Exactly. The set of the whole possible images is range. 그쵸? Set of the all possible tx or images is called the range of t. 그쵸? range of t. 자, 질문 좀 봅시다. 형민, which part are you trouble in understanding? or 형민 or 누가 있었지? 수연. 어디가 좀 어려워요, 여러분? 도메인, 코도메인, 이미지, 레인지 이런 것들은 사실 다 그냥 데피니션이에요. 그쵸? 그냥 우리가 이해를 하면 되는 거예요. 어렵긴 한데 우리가 뭐랄까 그냥 그렇게 부르는 거예요. 그냥 우리가. 그쵸? 자, AX 형태가 inconsistent 하다면 X는 리니어 트랜스포메이션이 아닌가요? 달라요. X가 리니어 트랜스포메이션이 아니라 A가 리니어 트랜스포메이션이냐 아니냐를 결정을 내리는 거예요. 첫 번째. 동인 학생. 그쵸? 그 다음에 AX가 inconsistent 하다면 자, AX가 inconsistent 한 거랑 리니어 트랜스포메이션은 사실 상관없어요. 이걸 보면서 얘기할까요? AX가 inconsistent한 게 아니라 AX equals C, AX equals B, 어떤 B가 정해져야 그게 솔루션이 아까 말했지만 도메인에 있느냐 없느냐가 결정이 나는 거죠. 그러니까 AX가 consistent하냐 inconsistent가 아니라 AX equals B or AX equals C가 consistent하냐 inconsistent하냐라는 개념이고, C가 레인지 안에 들어가면 consistent 할 거고, C가 또 레인지 안에 못 들어갔으면 inconsistent 할 거다라고 이해하면 돼요. 그렇죠? Any other question? We can move further if you in case that you fully understand what I mean so far. 아마 이제 여러분들이 이제부터 조금씩 개념들이 막 섞이기 때문에 여러분들 여기까지가 조금 이해를 해야 사실 다음을 또 넘어갈 수 있거든요. 조금 이해가 안 되는 친구들이 있으면 좀 지금 좀 얘기를 해봅시다. 괜찮나요? 자, 그러면 조금 더 해봅시다. Let me show one more example. For example, let's matrix A is 1031. Then the transformation T from R2 to R2 define the T of S, which is AX, just AX, which is called the short transformation. You don't need to memorize this short transformation, but this is just one of the transformation when A is defined 1031. Then it can be shown that if T act on each point in 2x2 square, then set of the images from a shaded parallelogram. So what does it mean? Okay, if A is 1301, one of the vectors X in R2 space here can transform to the another vectors by T of X or A times X. So for example, X was 1.5 and just 1, then AX to be the sum vector in codomain R2 space, right? If we think another point here, then it may be moved to looks like this. If we consider the whole point in 2x2 square matrix, this one is transformed to this kind of parallelogram. So maybe let's imagine you have this kind of shapes in domain. Then this shape is moved to the looks like this. This is codomain. So this is examples of the one of the transformation A. 그래서 뭐예요? 이렇게 스퀘어를 우리가 이렇게 뭐예요? 이렇게 평행사변형으로 옮기는 트랜스폼은 이런 형태, 즉 1방 3, 1로 형태가 구성된 A를 곱하면 이런 식으로 옮길 수가 있다는 거죠. 하나의 one of the examples of the transformation. 그렇죠? Let me show one more example. For instance, that's the continued examples. 그렇죠? 이거 설명하는 거예요. 그래서 if the image of the point U, just U is here, here, just image is here. 그렇죠? The A times U. 그렇죠? So if U is 1,2, then A U is going to be the 6, 2, or image of 2x2 is going to be the A times 2x2, so it's going to be 8 by 2. So T deforms the square as if the top of the square was pushed to the right while base is held fixed. So it's going to be just a parallelogram. So it looks like this. This is one of the examples. Yeah. So actually, this is just the transformation. Actually, this is the out of scope of this lecture, but I would like to show you where this kind of transformation used in the deep learning or the convolutional neural network that I work in this area. So this is just a supplementary, so you don't need to, you don't need to memorize all of these things, but there was the special transform network, which is called the STN in deep learning area. So what is the objective of this STM module is that, okay, you have the font, looks like this, but it has some kind of arbitrary transformation, looks like this. But to understand this digit, you have to make each images to this kind of unwrited version of the images. I mean, this untransformed version of images, which helps to improve the how to say, the recognition quality of the images. So this is called the STM. And to define the STM, special transform network, we have to find out one of the matrices defined in 2 by 3. A is equal to 2 by 3 space. So the objective of this STN is how to find the optimal matrix A in 2 by 3 space to transform your input data to input data. So this is the one of the examples that your linear transformation concept can be used in other research area. So if you are more interested in this kind of topic, I made some slide. So modeling the special transformation using the convolutional neural network. So if you're interested in, so you can see this, you can watch this video. So maybe you understand what I mean. 그래서 뭐 이제 뭐 여러분들 좀 어려울 거예요. 그래서 왜 뭐 우리가 막 이런 리니어 트랜스포메이션 뭐 이런 거 왜 배우느냐, 어디에 쓸 수 있느냐, 뭐 여러분들이 아마 컴퓨터 사이언스 이제 이 필드로 가면 여러 가지 분야로 가겠지만 그중에 이제 저희가 만약 딥러닝이라고 하는 인공지능이라고 하는 분야에서는 뭐 이런 데 쓰인다라는 걸 좀 보여주고 싶었고, 뭐 STN이라고 하는 분야가 있어요. 연구가 있는데 그 뭐 하는 거냐면 이렇게 숫자 인식인데 이렇게 숫자들을 카메라 딱 찍으면 뭐 이렇게 왜곡도 생기고 이렇게 뭐야 트랜스폼들이 돼가지고 이렇게 뭐예요 이렇게 막 노이즈도 섞이고 할 건데 이거를 이렇게 업라이트 버전으로 잘 바꿔주면 숫자 성능이 인식이 더 올라가거든요. 그래서 이제 이런 어떻게 트랜스폼을 할까라는 이제 뭐 연구들이 있는데 거기서 하는 게 사실 결국에는 A, X equals B예요. 그래서 이 A, 2x3 매트릭스, 그래서 이 좌표를 트랜스포메이션하는 2x3 매트릭스들을 어떻게 잘 찾을까에 관한 연구가 이제는 이러한 필드에서 일어나는 거고, 이제 그게 바로 이제 오늘 우리가 배우고 있는 리니어 트랜스포메이션 어플리케이션 중에 하나예요. 근데 뭐 여러분들 좀 어렵겠지만 관심 있으면 좀 이런 걸 좀 봐도 괜찮을 것 같고요. 네, 그렇습니다. So far we discussed transformation. Then let me present one more concept. Then when we say that our transformation is linear, so when we say that this is a linear transformation, so to become the linear transformation, the transformation T should satisfy two following statements. Then we can say that the transformation T is linear. So first of all, if T of U plus V is equal to T of U plus TV for whole U and V in the domain of T, then we can say that this is linear transformation. And T of CU is equal to C times TU for whole scalar C and whole U in the domain of T. this is second statement, right? So if some of the if arbitrary transformation T satisfy these two statements, then we say that this is a linear transformation. Linear transformation. So in other words, okay, let's suppose that this is a domain and this is a codomain. Codomain. Let's say here also U, arbitrary vector U and V, and let's say here was vector U and vector AU, 그렇죠? In this case, just think arbitrary vector T, arbitrary transformation T. So it's going to be TU and it's going to be TV. So this transformation T to become linear transformation should be satisfied previous two statements, right? So first one is that the sum of the T U plus V. So let's say here is U plus V. Then T of U plus V may be here. Then the first statement means T of U plus V should be same as TU plus TV. TU plus TV. One more thing is that if CU constant times U, scalar times U, then maybe T of CU is here. Right? If this is a linear system, then it should be same C times TU. So this is the definition to become a linear transformation. So in other words, the linear transformation preserves the operation of the vector addition and scalar multiplication. Vector addition and scalar multiplication. Then let's prove why we call matrix equation AX as a linear transformation. So why T of U or AU as a linear transformation? Let's prove. So to prove this, we just check this AX or AU satisfy previous two following statement. Let's just prove. So first of all, when we think about AUV, then by the properties of the matrix equation, AU, AV, then this is it's going to be TU plus TV. Right? From the properties of the matrix, right? So which was the TU plus V. So we easily say that first statement was satisfied, right? Second one is that TCU, ACU, it's going to be the CAU, it's going to be the CTU. So we also say that the second statement is also satisfied. So we can say that AX, one of the examples of the transformation AX is a linear transformation. 그래서 뭐예요? 우리가 이제는 어떤 arbitrary transform T가 이 두 가지의 성질을 만족할 때 리니어라고 하는데, 그럼 우리가 이제 이번 학기에 관심 있는 AX라고 하는 이 좌변에 AX equals B의 좌변에 해당했던 AX는 결국에 리니어 트랜스포메이더라. 리니어 트랜스포메이션을 부르더라. 왜? 이 두 개를 이렇게 증명해 보면 둘 다 만족하기 때문에 라는 거죠. 그렇죠? One more thing is that if T is the linear transformation, then T over 0 should be 0. And T CU plus CU plus DV should be CTU plus DTV for all vector UV in the domain T for whole scalar C and CT. What does it mean? Why this statement is true? Because if AX, in this case, X is equal to 0, right? So in this case, X times 0 vector is going to be 0, is that right? So T0 is equal to 0. Okay. And this second statement can be easily proved by, similarly, this procedure. So please prove this statement by yourself. So you don't need to submit this one, but please prove this statement similar to the here. 그렇죠? 이거를 우리가 AX인 경우로 한번 이렇게 여러분들 한번 증명을 해봤으면 좋겠어요. 알겠죠? 어떻게 너무 당연해요. 그렇죠? 이 두 개를 합치면 되죠. 그러니까 so let's say this equation is equation form. If a transformation satisfies previous equation form for U, V, C, T, it must be linear. And limited application of form produce a useful generalization. Not a just vector U and V, but you can generalize T of arbitrary set of the vector C1, V1, C2, V2, CP, V2 is equal to C1, T, V1, C2, T, V2, CP, T, VP. So in engineering or physics, it is referred to as a superposition principle. 슈퍼포지션이라고 사실 많이 불리는 건데, think V1, V2, VP as a signal that go into the system, and T, V1, VP is a response that our system or signal. So what does it mean? Okay. Let's suppose that you have a system, T of X, and your input is X here, and your output is going to be Tx, right? If your system is linear, for example, AX, linear system, then some of the vectors input V1, V2, VP can generate the sum of the output of T, V1, T, V2, T, VP, T, VP. Then if this system is linear, T, C1, V1 plus C2, V2, CP, VP should be same as CT, V1 plus C2, T, VT, CP, T, VP. Right. So this is a very, very important concept. So why you have to know the linear transformation or the linear algebra? So you want to understand your system, 그렇죠? Your arbitrary system, your black box system T, but you only have the input and output of your arbitrary system T. Then by just check this relationship, then you can just check your system is linear or not. Your system is linear or not. Anyway, the system satisfies the superposition principle if whenever all input expressed by linear combination of a signal, the system response is the same linear combination of the response to the individual system that I told you here. One more concept is given a scalar R, define T by Tx is Rx, not a matrix A, but just to make just scalar be R. Then in this case, this transformation T is called a contraction when R is smaller than 1, and dilation if R is larger than 1. This is just a extreme case of the system because it's not a matrix A, it's just scalar value. So in this case, this transformation T is called the contraction or the dilation. Okay. That's it. So one of the most important things that we can consider your matrix equation AS as a linear transformation. What is a linear transformation? When the transformation T satisfies this one. So to conclude, your AX, AX is a linear transformation이다. 그래서 써봅시다. We are interested in the AX equal to B. Then this one is a linear transformation. So we can use the many concepts defined in linear transformation to solve AX equals B. That's the topic of today's lecture. Okay? 그래서 이제 무슨 얘기를 한 거냐? 오늘 이제 1.8을 끝냈는데 뭔 얘기를 한 거냐면 결국에 AX equals B를 우리가 풀고 싶은 거야. 항상 했지만 AX equals B 우리 풀자 열심히. 풀다는 게 뭐예요? 솔루션 이그지스턴. 결국 두 개를 하고 싶은 거예요. 그렇죠? 솔루션 이그지스턴스. 솔루션 유니크니스에 대한 대답을 하고 싶은 거죠. 그렇죠? 그리고 솔루션이 존재한다면 솔루션을 찾고 싶은 게 결국에 솔루션 푼다는 거고 뭐예요? 그걸 하는 여러 가지 지금 작업들 우리가 이번 학기 내내 하고 있는 건데 오늘 배운 건 그 중에 하나 이 AX가 사실은 트랜스포메이션한 종류다. 어떤 X라고 하는 거를 일단 어떤 AX로 보내는 트랜스포메이션 종류인데 근데 특이하게도 리니어 트랜스포메이션이더라 라는 거죠. 왜? 방금 말했던 이 프로퍼티를 만족하기 때문에 그렇죠? 그래서 리니어 트랜스포메이션이더라 라는 거를 이제 우리가 오늘 배웠습니다. 퀘스천 서버. 자, 오늘 얘기했던 거 도저히 무슨 말인지 하나도 모르겠다. 손. 자, 이제 오늘은 더 안 나갈 거예요. 자, 우리 이제 여기까지만 하고 우리 좀 얘기를 좀 해봅시다. So, is there any who did not follow anything in today's lecture? 자, 그럼 오늘 했던 거 중에 조금 너무 이제 좀 따라하기 어려웠던 내용이나 아니면 조금 이해하기 어려운 내용 혹시 있었나요? 이다 학생이 트랜스포메이션 하는 이유가 아니요. 그건 아니고 그러니까 트랜스포메이션을 하는 이유는 그러니까 트랜스포 하는 이유가 따로 있는 게 아니라 그냥 우리가 시스템이 트랜스포메이션인 거예요. 그러니까 시스템 TX가 트랜스포메이션이죠. 그렇죠? 근데 그게 그 시스템이 리니어하냐 아니냐를 사실 판별해야 되는 경우가 많아요. 그러니까 리니어하면 그러니까 우리가 가지고 있는 블랙박스 시스템에 리니어할수록 더 우리가 가정할 수 있는 프로퍼티들이 많아지거든요. 근데 리니어한지 안 한지를 어떻게 알 수 있냐? 시스템이 어떻게 되는지 몰라요. X는 블랙박스예요. 근데 우리가 알고 있는 건 뭐냐? 인풋과 아웃풋은 알고 있어요. 그 시스템에. 뭐 V가 들어가면 TV가 나오고 V2가 들어가면 TV2가 나오고 쭉쭉 알고 있어요. 그럼 그때 우리가 인풋을 리니어 컨비네이션 해가지고 C1, V1 쭉 리니어 컨비네이션 해가지고 시스템에 넣었을 때 아웃풋이 각각의 아웃풋의 리니어 컨비네이션과 똑같다면 그게 이제 우리가 리니어 트랜스포메이션이라고 할 수 있다라는 거예요. 우리의 시스템. 알겠죠? 미안해. 제가 설명 잘못한 것 같아. 네. Other question. So, I will finish today's lecture here. Maybe some of you are very confused on this topic. So, I will upload our lecture after finishing this class. So, please recap and please go back to your textbook and try to understand what I mean, and let's fully understand what linear transformation is. Then let's move to the chapter 1.8, 1.9 next week. 알겠죠? 여러분들 너무너무 중요한 얘기를 오늘 하고 있는 건데 아마 이제 여러분들 조금 이번 학기에 처음으로 벡터나 매트릭스 배워보고 한 친구들은 조금 어려울 수 있겠다라는 생각은 계속 들은 것 같아요. 근데 그럼에도 어떻게 해야죠. 그렇죠? 그래서 올려줄 테니까 오늘 바로 올려줄 거니까 여러분들 복습해보고 책에 나와 있는 내용들 다시 한번 꼼꼼히 읽어보고 궁금한 거 있으면 조교님들 질문 메일도 다 알죠? 조교님들 또는 저한테 물어보고 완벽하게 이해를 하고 우리 다음 챕터 1.9로 넘어가도록 합시다. 알겠죠? Other question? No? Okay, that's it. So this is end of today's lecture and this is end of chapter 1.8. Next week, we'll move to the chapter 1.9, the matrix of the linear transformation. Okay? Okay, that's it. So this is end of today's lecture. Thank you very much and see you next week. 여러분들 오늘도 너무 수고 많으셨고 조금 여러분들 힘들어하는 것 같아서 개인적으로 너무 마음이 아프긴 한데 조금 잘 복습하고 우리 다음 주에 잘 따르고 갑시다. 알겠죠? 너무 고생하셨고 주말 잘 보내시고 우리 다음 주에 보도록 합시다. 고생 많으셨습니다.